Hi, my name is Nico and I'm author of the paper par-gem5, Parallelizing gem5's atomic mode. As the name already suggests, the gist of our work is a parallelized version of the full system simulator gem5. So if you have any stakes in System C, virtual platforms or other simulation-related topics, the following presentation might be of interest for you. But first, let us explore why parallel simulation has become such an important design tool.
In the year 1971, Intel released the first commercially available microprocessor, the Intel 4004. This processor, comprising only 2400 transistors, was the beginning of a technology race that is unmatched in the history of human endeavor. Fast forwarding to today, roughly 50 years later, state-of-the-art processors like Apple's M1 cram more than 15 billion transistors into a little piece of silicon. This is more than 5 million times the number of the 4004. The overall trend of this development is described by the well-known Moore's law. According to Moore, the number of transistors that we can put into a chip follows an exponential trend, leading also to an exponentially increasing system complexity. However, the single-thread simulation performance that we get from new systems is outpaced by this complexity. This means, with each new generation of microprocessors to be simulated, the simulations take longer and longer. While many engineers and scientists have proposed brilliant ideas to close this simulation gap, the most straightforward approach still remains parallel simulation.
So instead of using one thread to simulate our systems, we distribute the workload onto several cores on our host computer. Parallel simulation has been around since 50 years, and one can easily find a plethora of papers on this subject, especially when it comes to parallelizing System C. Yet, parallelizing gem5 is still an uncharted field of research. And with our work, we propose the first generally parallelized version of gem5. So speaking of gem5, what is it and what can it be used for?
gem5 is an open source full system simulator. It allows you to design custom compute systems and simulate them. To be more precise and already introduce some frequently used terms, the simulating computer is called host computer or host system. On this computer, you execute one or multiple instances of gem5. In each of these instances, you simulate your custom design, also called target hardware or target system. Accordingly, the software running on your target hardware is called target software. Since many people have at least some basic knowledge about System C, a frequent question is, how does gem5 compare to System C? Well, in fact, gem5 is pretty similar to System C in many regards. But instead of just offering a mere simulation framework like System C, gem5 provides an extensive library of different simulation models. For instance, let's assume you want to model an ARM-SoC. You could start by choosing an out-of-order ARM core as your starting point. Instead of just using one core, you could also make it a quad-core system. Now add caches in the main memory from gem5's model pool and wire it up. All of these models behave functionally correct, so booting up a Linux OS on your customized system should pose no problems. Also opposed to System C, the whole process of assembling a custom system is aided by a Python frontend. This allows to quickly test changes without requiring recompilation of your whole VP. If you want to get warm with gem5, I can highly recommend to visit the website and check out their learning section. In order to understand how we parallelize gem5, we now take a closer look at the inner workings of it. The fundamental principle of gem5 is a so-called Discrete Event Simulation, short DES. In a DES, everything is modeled using events that take place at discrete points in time. For example, event T0 could be the tick of a single cycle CPU. What you usually see in DES simulations is events scheduling other events. For instance, in gem5, the CPU tick not only implements the functionality, but it also schedules an event for the next cycle. This gives us some sort of dependency graph. And pretty much as in our own lives, edges can now reach back in time and events happen in a chronological order. If you would now assume a two-processor system, it might look like this. With default gem5, all of these events are executed in a sequential fashion, easing the adherence to causality constraints. But how do you do this in parallel? A simple approach is to allow parallel execution of events that happen at the same time. For instance, E0 and E3 could be executed in parallel as there is no partial order for a single point in time. However, due to the cycle-wise synchronization, This approach does not achieve very high speedups in practice. So, how did we solve this problem? Well, in our case, we decided to introduce multiple event queues. In our example, they correspond to Q0 and Q1. Each of these event queues refers to a single thread on the host computer and executes a certain chunk of the simulation. But this approach leaves us with problems such as, what happens if one CPU sends an interrupt to another CPU? To tackle this problem, we first introduce some global synchronization points at a period of delta Q, a parameter that we call the quantum. If you are familiar with the concept of temporal decoupling, this term might ring a bell. And in fact, our approach resembles temporal decoupling in a parallel fashion. Whenever there is now a schedule crossing the borders of event queues, we check if the event was meant to be executed in the same quantum. If so, we postpone it to the beginning of the next quantum. This seems like a drastic approach with possibly far-reaching consequences, because as you can see, events might now be postponed and processed out of order. However, especially in the context of full system simulation, a certain amount of delays and out-of-order execution impacts accuracy, but does not affect the functionality of your system. But more about that in a few slides. Next, we take a closer look at how the simulated system is mapped to event queues, because reducing the number of postpones and inter-queue dependencies is vital for having a fast and accurate simulation. An example for our chosen approach might look like this. As you can see, every CPU subsystem, including level 1 caches, is mapped to its own event queue. We chose this mapping as there is a frequent communication between level 1 caches and CPUs. All other components, like the level 2 cache, main memories, or peripherals, share a single event queue. This means if you simulate an n-core target system, n+1 event queues will be created. With this approach, we attain reasonable performance and accuracy, but ultimately, we keep the event queue assignment flexible. So if you're wiring up a simulation, you can directly control the event queue indices using Python. This allows you to quickly experiment with different mappings.
The performance achieved of this approach is depicted in the following graph. Here you can see the execution of a bare metal bubble sort benchmark using default gem5, here in purple, and par-gem5 with various quanta. On the x-axis we have the number of simulated cores, and on the y-axis we have the simulation performance in million instructions per second. What you can see is that we reached the maximum performance for 128 core systems, which is roughly a speedup of 20x. Of course, the maximum speedup depends on the number of cores, if you remember the n+1 rule from the last slide. Hence, par-gem5 only unfolds its true potential for very large many-core systems. Another thing that we can see on this slide is the relation between performance and the quantum. Remember, the quantum is the maximum simulation time after which event queues have to synchronize again. This means large values are beneficial for the performance, yet they might be detrimental for the system's accuracy. As you can see here, for simulations with quanta as low as 100 nanoseconds, there are already signs of a degrading performance. Yet just increasing the quantum is associated to diminishing returns. For example, there's basically no performance difference between a quantum of 10 microseconds and a quantum of 1000 microseconds. Thus, in order to find the optimal quantum, we have to take a closer look at accuracy. Until now, we have touched the subject of accuracy several times, but we never provided an exact definition for it. This is due to the fact that there is no single kind of accuracy. For example, when simulating with gem5, what you get in the end is a results file which easily comprises hundreds or thousands of different simulation statistics. And each of these statistics is a possible representative for the accuracy. So in order to simplify things, we assume that the target simulation time is a representative for the accuracy. We made this choice for a couple of reasons. First, the target simulation time is some kind of meta-statistic that accounts for other statistics as well. Second, the target simulation time is a popular simulation statistic that directly correlates with the achieved performance of the system. Anyway, we now take a closer look at the achieved accuracy results. Again, we have the bare metal bubble sort benchmark using default gem5 now in red and par-gem5 with various quanta. You can also see the number of simulated cores again on the x-axis, and on the y-axis we now have the simulation time or the target time in milliseconds representing our system's accuracy. Note that the regular simulation represents some kind of baseline at 100%. So what you can see is that simulations with a higher quantum tend to higher inaccuracies. For instance, the 64-core simulation at a quantum of 1000 microseconds basically overestimates the required simulation time by a factor of 2x. And as you can see, if we move to smaller quanta, this error will also get smaller. In the case of 10 microseconds, the measurement is basically indistinguishable from a regular ones. In general, the parallel simulation always tends to overestimate the required simulation time. We attribute this to our postpone approach, which leads to events and interrupts always being delivered later, but never earlier. So what we now did is that we used the regular time in order to determine the accuracy of our parallel simulations. However, requiring one regular simulation for each parallel simulation would of course undermine the performance benefits of our parallelization approach. To tackle this problem, we introduced some kind of analytical error estimation. So how does this work? For each quantum that we have, we check if there was a postponed event. If so, we accumulate this delay of the postponed event, which gives us some kind of worst case timing error estimation. Moreover, we could use this timing error and subtracted it from our simulation time that we obtained, getting some kind of corrected value. This corrected value is depicted here by these gray bars that you can see here. What you can see is that this corrected value is not always able to hit like 100% accuracy. What it tells you if a simulation was very inaccurate. For example, again a 64-core simulation, you can see that there's a huge discrepancy between the corrected value and the measured value, which tells you that this simulation was probably very inaccurate and you should maybe transition to lower quanta. We now showed the validity of our approach using some bare metal best case hello world benchmark. But of course it would be much more interesting to have some kind of real world benchmark with an underlying operating system. So we set up a Linux target with NASA's advanced supercomputing parallel benchmarks. This is a benchmark suite comprising 8 different supercomputing inspired applications. The results of these benchmarks are depicted in this graph. Again, we have the number of simulated cores on the x-axis and the speed up factor here on the y-axis. The quantum that we used was 1 microsecond. So what we can see here is a very heterogeneous picture. We have some benchmarks like EP that seem to scale very well. So as you can see, this blue benchmark here can achieve a speed up of roughly 12x. On the other hand, we have benchmarks like CG that already saturate at a speed up of 2.5 and cannot gain really much speed up from an increased core count or thread count. So what we observe is that pretty much as in real life, benchmarks that have a huge inherent parallelism scale very well with par-gem5. Vice versa, if your benchmark does not have a huge inherent parallelism, or if there's a lot of core-to-core communication, or if it frequently accesses shared resources, your benchmark cannot exploit the full potential of par-gem5.
We're now already near the 50-minute border, so let's recapture the most important points. With our paper par-gem5, we propose the first generally parallelized version of gem5. In the best case scenario, par-gem5 can achieve speedups of up to 20x while keeping inaccuracies in a single-digit percentage. With par-gem5, we have laid the foundation for many interesting and further questions. For example, what is the optimal quantum and how to determine it? We also plan to extend par-gem5 to the so-called timing protocol, which is similar to system-C's approximately timed style. So far, par-gem5 only works for gem5's atomic protocol,
which is similar to System C's loosely timed style. At this point, I would like to thank you for listening, and if you have questions, feel free to connect with us at the DATE conference.